Well, hello everyone. This is Aiden Mats in another video. Today, we are going to explain a bit how the MMC or Modular Multilevel Converter works. Basically, this was part of my master thesis that I did last July in 2025. And well, I want to basically explain what I did, and I will also show later my. Vale. I will later show the Simulink file and everything. So before starting with MMC, I want to show you my presentation a bit, like 5 minutes, just to understand what is the MMC and the basics and why we use this voltage source converter technology and we don't use other ones. I only studied MMC. I didn't study other topologies such as cascaded half bridge or even let's say predecessors of the MMC because this is basically the literature right now. I mean, if we want to apply voltage source converter technology to high voltage applications, we need to use this technology. So this is basically a bit of the introduction. Here I explained basically how this technology works, why we are stacking cells, and we are recreating this multi-level technology. First, because our IGBTs or our transistors cannot hold really high level voltages. We are talking that maybe nowadays we can find IGBTs that can hold up to 6 kilovolts, I think 5 kilovolts, I'm not sure, but this is the range. And of course, if we are talking about high voltage, we are working with 400 kilovolts, for example. We are transmitting this power, so the losses are really low when we are basically moving power. So here the idea is to stack a lot of cells. These cells are submodules. Basically, they are half bridge or full bridge single phase technology. And here the interesting thing is that our IGBTs are only holding up to the capacitor voltage. So if, for example, we are working with 400 kilovolts, as I said before, we only need to stack 400 cells of 1 kilovolt, and our IGBTs on each cell only hold up to that voltage. This is something really interesting because we can bring this technology, these high voltage levels for our voltage source converters. Before, I think the only manufacturer possible of doing this was ABB, and basically they were stacking a lot of IGBTs in one arm. One arm is basically, for example, if we are looking at the positive pole between the positive pole and the AC connection, this is an arm or a branch, okay? They were stacking a lot of IGBTs, for example, 400 IGBTs, and they were switching them at the same time. And this is really difficult because you need a really good modulation. If not, if you switch, for example, one IGBT and the other one is still not switching, then you will find a short circuit, for example, and you will burn up really a lot of things. But with this MMC, you don't need to switch at the same time. You're only bypassing, you're connecting the capacitor or disconnecting the capacitor depending on how much voltage do you want to reach, right? Because as you know, the AC wave is also changing at 50 years or 60 years, depending on the country and on the zone. So you need to recreate this superposition of AC and DC, and your voltage level will be changing depending on this thing, and also if you want to move the power from the DC to the AC or the other way around, right? So yeah, as I said before, the interesting thing here is that we have submodels, and the submodels we are modulating them, right? So we can give them any, let's say, PWM that we want. If we want to recreate an AC wave or a DC wave or an AC wave at a different frequency, we can do that. We have these degrees of freedom that we will talk about them later. Okay. And yeah, I think I can play this simulation here. Okay, as you can see, we have, let's say, the same circuit topology as I showed before. So this is basically an interconnection between two systems, in this case, two AC systems at different frequencies, okay? As you can see in the right part, we have a three-phase system at 2 Hz and a single-phase system at 1 Hz. And as you can see, if we look at the voltages at both ports, the bulbs that I connected showing, let's say, a resistance, they work only at the frequency of the original AC system, okay? But inside the converter, inside let's say the bulbs that are placed inside, they have a superposition of both frequencies, okay? And this is the same topology as the MMC or even a three-phase two-level converter. Instead of having cells, we have one IGBT, okay? But the topology is exactly the same. And as you can see, we have a superposition. This is important because we will have to deal with this later, okay? And as you saw before, we have capacitors in cell, so these frequencies can go inside the capacitor, maybe create ripple, and as we will see later, this is really important, okay? I think this is all that I wanted to explain about the introduction, and I will explain now a bit the analysis that I perform in my master thesis, which is a bit different from the analysis that has been, let's say, studied in the literature. At least I didn't find this analysis. This is something, I don't know, it's not new because it's analysis from something that is already, say, used. Okay, this technology is used, but at least another point of view, right? So this is the topology of the MMC just for one arm, okay? And the superposition of all the cells, I'm showing it as an AC source. This is not really true because, as I said before, we are recreating an DC plus and a DC, sorry, plus an AC. So this is basically an AC with a offset, all right? But I only showed as an AC just to check that. We have also the AC wave here, and yes, one leg, okay? So we have two meshes, basically Kirchhoff voltage laws. We can recreate these two equations, considering the voltage drop in the inductances. We are not considering resistances to simplify a bit the analysis and to make the equations a bit compact, but the idea is the same. And we get this system of equations and we, let's say, translate it in matrix, in arrays, okay? Why? Because we are going to apply some algebra laws, so we need to put this matrix so we can basically organize a bit the equations, okay? So we're multiplying the the sorry I don't know, okay, now, so we are basically multiplying the currents by the say the impedances or inductances, and we are letting the voltage in the other side of the equation. So this is an equivalence, easy equivalence, and now we will study the impedance matrix. Why? Because the idea here is to find a decoupled system to basically, let's say, decouple the two equations and find new equations that we can use separately. And as you can see in this impedance matrix, we have coupling terms. Why? Because as you can see, or as you may know, when we multiply, when we are performing, sorry, a product of vector by a matrix, we multiply like this with this row from this column. So we are multiplying both impedances LA, Larm, and LG, Lgrid by the two currents. So we find these coupling terms. The idea here is to find a diagonal matrix. Why? Because if we have a diagonal matrix, then later we can multiply this diagonal matrix by a current vector, and we will find this decoupled system, and we will use it to actually control the converter. Okay, this is something that you have to trust me now, and later I will explain better why this can happen, right? So we will perform the equation that I'm showing you in the top right part. D equals to P minus 1 MP. M is the impedance matrix, so we need to find a eigenmatrix formed by the eigenvectors of M. Okay, and this basically is, I did it with MATLAB. There are some, let's say, some functions that allow you to find this, but you can do it let's say, by pencil, and you will find this result. Okay, this is the eigenmatrix. So if we perform the equation, we will find finally this diagonal matrix, and this is important because this eigenmatrix allow us to rotate the matrix, the impedance matrix. Why? Because the D let's say that the matrix D and the matrix M are said to be similar. So they are giving exactly the same information but in another language. And this translation is performed by these eigenmatrix arranged by the eigenvectors, the proper vectors of M. Okay, you can find more information about this in the internet. I'm not going to be to explain further about that. Okay, but basically we are transforming the matrix. And as you can see, this is the logic that we are following. We have, let's say, the equations in one, let's say, space, okay? And we transform it using these eigenvectors to the decoupled system. So once we have this diagonal matrix, we have to transform also the current vector and the voltage vector to this new system to let's say to explain or to show everything in the same language. You can see it as a language, okay? We pass this from Spanish to English, but these two currents and voltages are still in English. So we need to translate it to Spanish to have everything in Spanish, okay? To have everything in the same space vectorial. So we transform it easily and we find this system representation. So we have this matrix decoupled, two new current vectors and two new voltage vectors. Sorry. Okay, so far we have this, and if you take a brief look, you will find something really interesting and something that happens obviously also shown in literature is that you can basically decouple the AC side from the DC side with these equations, and you can control the two ports, let's say the interconnection between the converter and these two ports in a decoupled way, in a separate manner. As you can see, if you perform this product, you will find the LA grid multiplied by these currents, this sum of currents, okay? And this will lead us to these voltages. And here we don't have the AC term, we will have the DC term. Okay, so we will use this equation to control the power exchange with the DC grid, controlling the offset between these two systems. And for the AC side, the same. We don't have the DC term because we are using something that you didn't mention. We are using a DC symmetrical monopole configuration. If we were using a asymmetrical configuration, this will change, of course, because we have, as you can see here, minus BDC divided by 2 and minus BDC divided by 2. And when you perform this product, this DC term gets cancelled here. So let's say if you have let's say a symmetrical configuration between the DC upper and lower, positive and negative, you can use these equations, okay? But once you have an unbalance, then this may change, and you will have here DC term, and you will need to deal with this, and then this is something that I had to mention, okay? But here we are using symmetrical monopole, balanced, same upper and lower, positive and negative, so this happens, okay? And for the three-phase system, we perform basically the same. So we have now 3 legs or 6 arms, sorry, 2 per leg, and upper and lower A, upper and lower B, upper and lower C, and we find this, let's say, this matrix representation. Here we don't have a decoupled system, so we perform the same analysis. We find this decoupled matrix. Okay, we transform later the voltage and the current vectors. Okay, so once we have performed this, here now we need to rename the variables, or we will rename the variables. Why? Because we will use these new variables to control the converter, and it's easier to rename them, sorry, to actually work with them, okay? So when we find let's say the additive currents, or the sum between the upper and lower, with the upper and lower arms, we will call them sum, and when they are differing, we will call them diff, okay? And for the voltage is exactly the same. So we find these 6 new equations, or 2 different system of equations, each one controlling the DC or the AC, okay, system. And Yeah, with this, we more or less are following the literature with another path. We are finding the same results. So this is something that's really good because with this we can, let's say, we can say, okay, we have done this analysis. We have find the same results. So we need we have to prove. We don't have to prove because we know that the results lead to the same way. So they're fine. Okay. And for the decoupled circuits, we have the additive and the differential circuit. As if you basically analyze these equations, you can find this new circuit. We have the DC terms, the impedances, and the, the voltages that we are say, creating, right, with our submodels, our cells. And for the differential circuit, we basically perform the same. And as you can see, this is basically an interconnection in it's the average model between a voltage source converter and an AC grid. So this is really easy. And with this new impedance, we can control the active and reactive power exchange. Okay, so with this, I think we are good to start analyzing our Simulink. We, I will explain you later this. This is, I think, for another video, maybe the second video. This is the introduction. We have arrived until the, let's say, the coupled equations. So we can now start understanding the Simulink model, okay? So this is basically what I built. We have the AC grid, we have the DC grid, and we have the converter in the middle, the interconnection, and then we have different blocks. We have the current controller, the energy controller, scope, so we can see if everything is working fine, and obviously the PWM, okay? And the reference that we are giving to each cell. One important thing here is that we are only using one cell per arm, okay? So we are working, let's say, with low voltage ratings. Why? Because if this works, then we only need to stack the remaining cells to reach this high voltage, and then obviously change the modulation. Here we are using a sinusoidal PWM, really basic. But if you are working with a lot of cells, you need to change the modulation. You need also, you have the same degrees of freedom, okay, but you can, for example, exchange the let's say the power between the cells of the same arm. This is something that here we are not. You can exchange power between the upper and the lower arms, as we will see later, but you only have one cell per arm, okay? But if this structure works, then let's say the 90% of the work is done, then you only need to start analyzing the new modulation, let's say. And yes, these new modulations that I don't remember now, the nearest level, I think, because here we, if we are working with a lot of cells, you don't need to actually switch at a high frequency. You can switch maybe at 500 Hz. Here we are switching at 10 kilohertz, I think, or 20 kilohertz even, and this is a really high frequency. Okay, so you don't have this. You have this package harmonic on the current, but at really low high frequency. Okay. Yeah. So after this done and set, here we have for the AC grid, I basically emulated basically an infinite bus. We have here the L filter, okay, the filter that we need between the converter and the AC grid. But I'm not even simulating here a Thevenin. This is an infinite bus, okay. This, because the idea here is not actually to see how the converter can perform with low, let's say, for example, a weak AC grid. Here we only need to know if the converter can perform correctly to the AC grid, or even we can simulate a fault, as we will see later. And here we can see if the converter can still be connected to the AC grid and give support until the AC fault recovers, let's say, okay. And for the DC, obviously we have also an infinite bus, okay, ideal DC grid. And yeah, so for each arm I placed a cell, as you can see here, and this cell is basically for IGBTs. I'm using a full bridge configuration. You can use a half bridge configuration. And you can basically see the difference, which is not really high. The difference comes when you have a DC fault, okay, when your voltage on the DC grid gets really low. I will explain it later. but I'm using also for the normal cases full bridge configuration. Okay, the capacitor is at 800 volts, I think, yes, and the capacitance is 1 e minus 3. Okay, so yes, if you want to start analyzing the MMC, I will recommend you to use it with DC voltage source instead of capacitors. You put here DC, sorry, a voltage source. Yes, for example, this, or maybe a controlled voltage source also is good. Why? Because I would recommend you to start analyzing it in an open loop with no control, just trying to establish a desired power flow between the two ports, and then you will start adding a current controller and an energy controller. At least this is how I did it. Understand it from the beginning, okay? But yeah, you have these 6 arms, and obviously these are blocks to get information out. I think it's called, yes, to workspace. Okay. So this is basically this first video. I showed you basics of the MMC. In the next video, I will start explaining the current controller, the energy controller, the modulation, and everything. So I hope you guys like it. Leave a comment if I have to, sorry, to explain something more slow, because of course I think I'm addressing this to people that have notions on power electronics a bit. Of course, not really much. I mean, I started this basically understanding buck boost converter, full bridge, single phase. I mean, not something really. I mean, the basics of power electronics. Okay, so you don't need to worry about this. And yeah, for the next video, I will keep explaining you the, the, the next notions. Okay, so goodbye, guys.